Okay, so we're moving to basic probability. We've already talked about probability has to be between 0 and 1. You can't have a negative, and you can't have a probability greater than 1. So we have a few definitions to talk about. One is random phenomena. Random just doesn't mean it's anything that can happen. It means we know what could happen, but we don't know which will happen. So when I flip a coin, I know that I can get heads or tails, but I don't know which one will happen. Because I don't know which one will happen, that is known as being random phenomena. It's kind of like when I roll a dice. I know I'm either going to get a 1, 2, 3, 4, 5, or 6, but I don't know what's going to happen. So because I don't know what's going to happen, that's called random phenomenon. So we know the possible outcomes, we just don't know which one we will get. As we showed in the other video, sample space is a list of all possible outcomes, and we did several of those. Law of large numbers, put a big star by this. This is really important. And basically it says, as we do something over and over and over again, what actually happens is going to get really, really close to what we believe will happen, what we expect to happen, or to the theoretical. So as we do it over and over again, things will start to get close to the theoretical. For instance, if I were to flip a coin 3 times, well, first off, you expect to get heads. You expect to get heads 50% of the time. But if I flipped it 3 times and all of them were tails, people might go, but no one would be really upset about it. It wouldn't be that unusual. But if I flipped it 300 times, people would be really surprised, and they go, you know what, there's something wrong with that coin. Further, if I flipped it 3 million times, they'd be even more surprised. In fact, the more I flip it, the closer it's actually going to get to 50%. Now, it may not be exact. It may be off by 3 or 4 or 5 or 6. But in the end, when I flip that coin, it's going to be somewhere between 49.9999 and 50.0001, which is really close to 50% if I flip it 1,000,000 times. Fortunately, I'm not that bored yet, so I'm not going to flip it 1,000,000 times. Probability distribution. That's a list of all possible outcomes of an event. And they're all going to be between 0 and 1. And when you add up all the possibilities, they're going to sum to 1. So when I flip a coin, I can get a heads or a tail, and that's 0.5, and this is 0.5. They're between 0 and 1, and if I add them up, they sum to 1. And that's all that's saying, okay? To be a valid probability distribution, it must sum to 1 whole. Complement. That's the probability an event will not occur, all right? And if they say, what's the probability something will not occur? You need to think 1 minus. So the key with a complement, and by the way, I'm not going to ask you what a complement is. You just need to know 1 minus, all right? So if you see not, I want you to think 1 minus. What's the probability of not rolling a 3 on a 6-sided dice? Well, that's 1, 2, 3, 4, 5, 6. There's my sample space. And so probability of getting a 3 is 1/6. The probability of not a 3 is 1 minus 1/6, or 5/6. All right? So this is what they're asking for, and all I did was 1 minus that. And you're going, well, Mr. Spencer, couldn't I just count it up and gone 1, 2, 3, 4, 5? And the answer is yes, you could. So if you would have written just 5/6, that would have been fine. But please remember, not means you're doing 1 minus. So what's the probability of not drawing an ace from a standard deck of cards? First off, you need to know a standard deck of cards has 52 cards, and that there's 4 of them in the deck. So not drawing an ace would be 1 minus 4 over 52. Well, I can make that a 52 over 52 minus the 4 over 52. That's supposed to be an arrow. And 52 minus 4 is 48. So I end up getting 48 out of 52. Wow, that's bad. 48 out of 52. This would be my answer. But I would need to show this somehow. And probably 1 minus 4 out of 52 is what you should show. If I draw 3 cards without replacement, what's the probability that none are aces? Well, I'm going to use this information. All right, so I'm drawing 3 cards. Well, what's the probability that the first one's not an ace? Well, we just said not an ace is 48 out of 52. Now this gets a little tricky. We drew a card without replacement, so now there's only 51 cards, and 47 of them are not aces. We drew another card, and so there's 50 cards, and only one of them, and so now we have 50 cards, and 46 of them are not aces. And then we could just go ahead and multiply that out. All right, the at least problems. At least problems are the most difficult questions I think there are, all right, or at least for my students. So when you see at least, I will always want you to think 1 minus opposite of what they asked. 1 minus the opposite of what was asked. So if a student guesses on a 5-question multiple choice quiz with 4 answer choices, what's the probability they get at least 1 wrong? First off, we have 4 answer choices. That means we could have a wrong answer, a wrong answer, a wrong answer, a correct answer. So basically, the probability of correct is 1/4. The probability of wrong is 3/4. Now, we have 5 questions, so we could get 0 wrong, 1 wrong, 2 wrong, 3 wrong, 4 wrong, or 5 wrong. They said at least 1. So if I get 1 wrong, that's fine. If I get 2 wrong, that's fine. 3 wrong, 4 wrong, 5 wrong. All right. But this would be getting none wrong, which means getting all of them correct. We have 5 questions, so I need 5 multiple choices, 5 blanks. And since they asked about wrong, I need to do the opposite of wrong, which is correct. Opposite of wrong is correct, and that happens 1/4 of the time. I'm just going to put 0.25. And I said it was 1 minus. So 1 minus that. And it turns out I end up getting a decimal answer of 0.9990. So if you're guessing on a 5-question multiple choice test, the chance that you get 1 wrong is almost 100%. It's 99.9%. That's crazy. So basically, please study. All right. And once again, they asked for wrong, so I did the opposite, which was correct. Because wrong was 3/4 and correct was 1/4. They asked for wrong, I did the opposite, and then I subtracted it from 1. So here we go. Probably the most difficult problem that we will see this year. Not the longest, but the most difficult. A machine has 4 components. The probability that the components do not fail during the year is 0.97, 0.99, 0.98, 0.96. If any component, this means at least. If 1 fails, the machine fails. If 2 fails, the machine fails. What's the probability that it fails? All right, so if at least 1 fails, the machine fails. So we know because it says at least, because this is an at least problem, it's going to be 1 minus. Well, they asked for fail, so we do the opposite of fail, which means it works. Well, the 0.97 and the 0.98, etc., those are works. This is works, 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 works. This is not fail. So 1 minus the opposite of fail, which is works. So 1 minus the bracket 0.97 times 0.99 times 0.98 times 0.96 equals 0.0965. So there's about a 10% chance that this machine will fail at some point during the year. Okay, the next video will be on expected values.